Welcome, deep divers. Today, we're jumping headfirst into something, well, fundamental, but also really persistently tricky in software security. Especially, I think, for those of you tuning in who are building the next wave of AI-powered systems, we're talking about insecure output handling. Now, for years, we've all heard the mantra, never trust user input. And look, that's absolutely still vital, non-negotiable. But with the pace of innovation, especially in AI, and how distributed our systems are becoming, that principle just isn't enough anymore. It needs a serious upgrade. We're really in a new phase where the unpredictability of these intelligent models, the complexity of microservices, it demands a much broader view on how we handle anything that leaves our systems. Okay, let's unpack this. We need to really get why this isn't just critical, but why it fundamentally changes how you as AI engineers need to approach security.
Yeah, and what's fascinating here and often gets missed is that insecure output handling isn't some, obscure vulnerability class. It's broad. It's often misunderstood. And it touches everything from like standard web apps we've dealt with for ages right through to the cutting edge AI systems you're architecting right now. And this deep dive, it's super relevant because as AI engineers, you're dealing with outputs that aren't deterministic. They're probabilistic. They come from these incredibly complex models. And the security implications, if you just implicitly trust that output, they're not just serious. They can be frankly catastrophic. We're talking about flaws that, if you don't address them, could turn your amazing AI innovation into, well, an unwitting tool for attackers.
That's a really powerful way to put it. So our mission today for you listening is pretty clear. We want to go beyond just definitions. We want to arm you with a really solid, clear understanding of what insecure output handling actually is, why it's so dangerous, particularly in the context of modern apps and AI, where these vulnerabilities tend to hide in those complex architectures you're building. And most importantly, how you can detect them, sure, but more crucially, how you can prevent them. We're aiming for actionable insights here, stuff you can take away and apply directly as you're architecting, building, and securing your AI solutions. It's about moving beyond just knowing the risk exists to really internalizing it and actively mitigating it in your daily work.
Okay, let's dive right in then. We've all had never trust user input drilled into us, right? It's been in the secure coding playbooks forever. But you're saying while that's essential, it's just not the whole picture anymore. So what exactly is insecure output handling, and why does it demand this paradigm shift, as you called it, in how we trust data, especially for AI engineers?
It really is a fundamental shift in thinking. Input validation is critical, don't get me wrong. But the modern reality, particularly with LLMs in the mix, means we have to evolve that mantra. It needs to become something more like, never trust data being sent to an interpreter. See, it's not just about when data first comes in. It's about the final step, the construction of any output stream. Think about it. Your app might be generating HTML for a browser, maybe JSON for a front-end framework, perhaps a shell command for the OS or a SQL query, or even dynamic content churned out by an LLM. If that data is going to be interpreted by something else, a browser, a database, an OS shell, another API, you've just crossed a critical security boundary. And that boundary demands, well, extreme caution.
That's a really key distinction. It's not just the origin, it's the destination and how that destination will process the data. It sounds like essentially a zero trust model applied to data flow itself. But what's really interesting here, I think, is how the perceived intelligence of something like an LLM can make developers drop their guard. We almost start treating its output like it's, authored content from a trusted colleague, not just another data source. That's a cognitive bias, isn't it? A dangerous one we need to fight against.
Precisely. And that cognitive bias is really at the heart of this paradigm shift in trust. A lot of developers, and look, AI engineers are definitely susceptible here too, they mistakenly assume that once data has been processed internally, maybe pulled from a trusted database, or even generated by their own carefully fine-tuned LLM, they assume it's safe for output. That's a fundamentally flawed assumption. That data, seemingly trusted, could have been polluted way back in its life cycle by malicious input, stored in a way that looked harmless, so when it's retrieved later and sent downstream, it's carrying this hidden payload just waiting for an interpreter to execute it.
Right, like a time bomb.
Exactly. And the evolution of application architecture just makes this even more critical. Think about older monolithic systems. Data paths were often shorter, more controlled, usually within one code base now. We've got microservices, complex client-side frameworks like React or Angular, third-party APIs everywhere, and of course LLMs adding another layer. Data flows are incredibly complex now. Data crosses numerous trust boundaries. Something validated way back at the initial entry point might get transformed, aggregated, stored, then retrieved and sent to a totally different kind of interpreter.
Like sending something initially meant for HTML display suddenly into a shell command context.
Precisely. This complex journey means security can't just be a gate check at the start. It has to be continuous. You have to ensure data is safe for its next specific destination at every single handoff. This is why that zero-trust data flow model is absolutely the cornerstone for secure output handling in any modern distributed AI-driven system. You just can't assume safety based on origin anymore. That really hammers home a crucial point then. If we're adopting the zero-trust view of data flow, we absolutely need to nail down a distinction that often gets blurry. The difference between insecure input handling and insecure output handling. People often mix them up, but they target different stages, and critically, they need different controls. Can you break that down for us? Maybe use some classic examples so we can see the difference in action.
Absolutely. It's a vital distinction because applying the wrong defense is almost as bad as applying no defense. Let's use two classic examples. For insecure input handling, the textbook case is SQL injection, SQLi. The primary target here, it's usually the server-side database, the attack mechanism. Malicious input, crafted by an attacker, fundamentally changes the logic of a back-end command. The classic example is putting something like AR11 into a login field.
Right, which gets jammed straight into the SQL query string.
Exactly, and it turns a simple select meant to find one user into something that just returns true, bypassing authentication. The typical impact, it's severe. Data breaches, obviously. Unauthorized changes or deletion of data, bypassing logins, sometimes even full server compromise. The database permissions are too broad. The core prevention, it's all about input validation and parameterization. First, you treat all input as potentially hostile the moment it arrives. Validate it strictly type, length, format, use allow lists, but the crucial part is using safe APIs, like parameterized queries or prepared statements. These force a separation between the code, the SQL command, and the data, the user input. The database driver handles the input as data only, preventing it from being executed as code. Okay, now let's contrast that with insecure output handling, and the quintessential example here is cross-site scripting, XSS, the primary target. It shifts completely. Now we're aiming at the client side, usually the user's web browser or maybe another downstream interpreter like a rich text editor or a mobile app's web view, the attack mechanism. This happens when malicious data, which could have come from user input, a database, an API, or yes, even an LLM gets included in the application's output without being properly encoded for its specific context.
So the browser receives it.
And the browser trusts the source website, right? So it just executes the script. If the server sends back script teller document.cookie script embedded in the HTML, the browser runs it. Simple as that. The typical impact, XSS can lead to session hijacking, stealing cookies to take over a user session, account takeover, stealing data displayed on the user's screen, defacing websites, or even phishing attacks launched from the trusted site itself. The core prevention. Here, the absolute key is output encoding. You treat all data heading towards an interpreter as untrusted, and you encode it specifically for the interpreter's context. This turns potentially dangerous characters like echo into their harmless display equivalents like enelt, intertatos, and napos, end quote. It prevents the interpreter from seeing them as code, and it's really vital to grasp that attacks often combine both. An attacker might inject malicious input, say a JavaScript snippet into a profile field, which gets stored harmlessly in the database. But later, when that data is retrieved and displayed as output to another user without proper encoding,
boom, stored XSS.
Exactly. It becomes an active XSS vulnerability. This clearly shows why input validation, while absolutely necessary, is not enough. Context-aware output encoding is a separate mandatory control you need at the output boundary. Ignoring this fundamental difference is where so many defenses fall down.
That distinction really clarifies why this zero-trust data flow thinking is so critical.
Mm-hmm.
Knowing where the vulnerability manifests, input or output, and understanding the target server database or client browser or something else dictates the precise defense you need. It's definitely not one-size-fits-all, especially now with apps pulling and pushing data from everywhere, include those unpredictable LLMs. Okay, we've nailed down the core ideas and that crucial input versus output distinction. Now let's get into the really scary stuff, the actual impact. So what does this all translate to in terms of real damage? What are the truly catastrophic things that can happen when these insecure output handling flaws get exploited?
Right. The consequences, as you hinted, they can be severe, and they ripple outwards. The specific damage really hinges on what downstream component ends up interpreting that malicious output. For instance, if the target is something client-side, like a user's browser, the most common things we see are cross-site scripting, XSS. This is still the heavyweight champ of web app vulnerabilities, a classic client-side injection. An attacker tricks a website into delivering malicious script along with legitimate content. It happens when an application takes data, could be from a user, your database, or increasingly generated by an LLM, and embeds it in an HTML response without properly validating or encoding it first.
And the browser just runs it.
The browser has no reason not to. It trusts the website it came from, so it executes the script. And because that script runs within the context of the trusted site, it blows right past the browser's same origin policy protections. This gives the attacker access to cookies, session tokens, anything the browser stores for that site, leading to session hijacking, basically, taking over the user's logged-in session, account takeover, stealing sensitive data right off the page, defacing the website, or even installing malware via drive-by downloads. It's incredibly versatile for attackers. And closely related, sometimes even sneakier, is content spoofing, also called content injection or virtual defacement. Here, the attacker injects arbitrary text or HTML, not necessarily script, to change what the user sees on the page. They exploit the user's trust in the site.
So, like putting up a fake login form?
Exactly. Or displaying misleading financial data or false instructions. The key here is that it doesn't always need JavaScript execution. Even if your app is rock solid against script injection through encoding, it might still be vulnerable to text-based spoofing if it just blindly outputs unvalidated text that looks legitimate. Imagine an LLM outputting slightly altered instructions in a medical app or wrong numbers in a financial report. It undermines trust, leads to bad decisions. It's a different kind of damage, but still very real. Now, things get significantly more critical when the downstream interpreter is on the back end. Here, we're talking direct server compromise, escalating the risk dramatically. Remote code execution, RCE. This is, without a doubt, the most critical impact, the nightmare scenario. It happens when attacker-controlled output from your application gets passed directly to a system shell, or maybe an interpreter function like exec in PHP or eval in Python or JavaScript. Yeah, if an attacker can manipulate that output, they can run arbitrary commands directly on your server, potentially a full system compromise. For you AI engineers, picture this. An LLM, tricked by a clever prompt injection, generates a shell command or a Python eval snippet, and your backend system, processing that LLM output, just executes it.
That's a direct line in.
A direct, unmitigated path to RCE, full control of your server via the LLM's output. Then there's server-side request forgery, SSRF. This pops up when your application uses output data to construct a URL that the server then fetches. An attacker manipulates this output to make the server request a URL pointing to an internal private resource,
Turning your server into a proxy for them.
Exactly. They can use your vulnerable server to scan your internal network, access sensitive data from internal services not meant to be public, or even hit cloud provider metadata endpoints. Those metadata endpoints are gold mines, temporary credentials, instance roles, an LLM outputting a malicious internal URL that your server then blindly tries to fetch. That's a prime SSRF vector, potentially exposing your entire cloud setup. And finally, privilege escalation. If manipulated output gets used as a parameter to some privileged function internally, an attacker could exploit that to do things they aren't authorized for. Maybe access another user's data, trigger admin functions, or even elevate their own privileges within the app. Imagine an LLM generating an instruction that, if handled badly, tells a backend system to change a user role or grant access to restricted data. The attacker basically gets the keys to the kingdom through the manipulated output.
Wow. Okay. So the impact spectrum is incredibly wide. It really runs the gamut from, messing with the user's browser all the way to complete server takeover. And it sounds like the probabilistic, unpredictable nature of LLM outputs just throws gasoline on this fire, adding huge complexity and risk. It's not just about stopping XSS in a comment anymore. It's about stopping your LLM from enabling RCE on your production servers.
Exactly. And this risk isn't static, is it? It shifts and changes as our technology does. And here's where it gets, I think, really interesting for our listeners. How do different application architectures, especially those using AI, create new and sometimes unexpected places for these vulnerabilities to hide? What does this expanding attack surface look like today, especially for AI engineers?
Absolutely. The attack surface is constantly morphing. Relying on old assumptions means we'll develop blind spots. Let's break down where these flaws typically lurk, starting traditional and then really focusing on the specific challenges LLMs introduce. First, traditional web applications. This is the classic battleground. Think server-side rendering, PHP, Java servlets, Ruby on Rails, older ASP.NET. The server builds the entire HTML page. Insecure output handling happens when data you can control or data derived from it gets slapped directly into that HTML string without the right encoding for where it's going.
Common spots.
Search results pages where the query gets echoed back, user profiles displaying user-provided names or bios, and of course comment sections, forms prime territory for stored XSS if that output isn't handled carefully. The critical point here, even for understanding modern systems, is the need for context-aware encoding within that single HTML page. Just doing basic HTML encoding isn't enough. Data inside a div needs HTML entity encoding. Data inside an input value needs attribute encoding, inside script tags, JavaScript encoding, inside style, CSS encoding, inside a URL, URL encoding.
So you have to match the encoding to the specific interpreter context.
Precisely. Failing to apply the correct encoding for the specific location is key. Many clever XSS attacks exploit these context mismatches, even if some encoding was applied. For an AI engineer whose LLM might generate HTML snippets for, say, a legacy UI, getting this fundamental right is vital. Okay, now let's pivot hard to the rise of large language models, LLMs. A new frontier of unpredictable outputs. For you, as AI engineers, this isn't just more of the same. It's a genuine paradigm shift in output handling risk. Why? Because unlike traditional apps with deterministic logic, an LLM's output is probabilistic, unpredictable. It generates content based on patterns, not explicit rules.
Which creates new problems.
Several unique and critical ones. A major failure mode we're seeing is developers mistakenly trusting LLM output, assuming it's safe, maybe pre-sanitized because, it's intelligent.
Big mistake.
Huge mistake. Dangerous assumption. An LLM can be manipulated through its input, that's prompt injection, which OWASP flags as LLM01, their top risk for LLM apps. You trick the LLM into generating malicious output that helps the attacker, and the attack vectors here are diverse, severe, and highly relevant for you. Client-side code injection, LLM-driven XSS. An attacker crafts a prompt telling the LLM to return JavaScript. If that output gets rendered in a web UI, a chatbot, a dynamic content block without proper context-aware sanitization. Classic XSS.
So the chatbot itself delivers the attack payload.
Exactly. Your helpful chatbot suddenly pops up script alert script, running in the user's browser, stealing their session, their data, whatever. The LLM created the attack vector, server-side code injection, LLM, as RCE vector. This is where the risk really ramps up. If your LLM integrates with back-end systems, maybe through plugins, function calling, or just generating parameters for internal tools, an attacker could trick it into generating malicious SQL, shell commands, or API parameters. If that output gets passed directly to a backend interpreter without super strict validation, you're looking at database compromise, RCE on your servers, unauthorized API actions.
Like the LLM spitting out drop table users or os.system, RMOS-RF.
Precisely those kinds of nightmare scenarios. The LLM becomes the weapon for server-side compromise. Sensitive information disclosure, LLM-powered data exfiltration. LLMs can accidentally leak sensitive data in their responses, maybe from their training data, or more likely in real apps from the current session context, like documents fed into a RAG system.
So it just blurts out confidential info.
It can. Ask it an innocent question, and instead of answering, it might hallucinate and provide snippets of internal documents it saw during training or context loading. PII, proprietary logic, trade secrets, direct data exfiltration via insecure output. Misinformation and hallucinations. Logic flaws. LLMs are known to hallucinate, generate plausible but wrong or nonsensical info. They also amplify biases from their training data. If this output is presented as fact or used to drive automated decisions, it becomes a huge security, ethical, and business risk. Flawed business logic, bad financial decisions, reputational damage. It's not code injection, but it is a critical output handling flaw in an AI context because the meaning, the logic of the output, is compromised. Think about the trend. Application architecture decentralizes output decisions, while simultaneously the output itself from LLMs becomes more unpredictable. Monoliths had central templating. APIs and SPAs created a responsibility gap who encodes client or server. Mobile added local storage as a new output target. LLMs are the peak of this. The output isn't just data, it's potentially code, commands, or prose with unpredictable structure, generated probabilistically. As systems get more distributed and intelligent, securing outputs gets exponentially harder. You need extreme suspicion for all generated content.
That is a genuinely sobering thought. That responsibility gap with LLMs, it needs tackling head on, right? From architecture design through the whole life cycle. It's a completely new game where the AI itself can be turned into the weapon.
Indeed. And beyond web and LLM specifics, we also have to think about mobile versus web applications. Web apps mostly target browsers with XSS. Mobile apps. They're binaries on potentially untrusted devices, so the risks shift. Beyond just XSS and web views, insecure data storage. OWASH's P Mobile M9. This is a big one. Sensitive data output by the app gets stored insecurely on the device files, logs, databases, shared preferences without proper encryption or access controls. The downstream component is the phone's file system, potentially accessible by other malware or someone with physical access. If your LM-powered mobile app stores chat history or sensitive generated content locally, big risk. Insecure interprocess communication, IPC. Mobile OICs let apps talk to each other. If your app outputs sensitive data via an insecure IPC mechanism, like an unprotected Android intent or content provider or an iOS URL scheme, another malicious app could intercept or inject data. Insufficient input-output validation. OWASH Mobile M4. This is broader, covering general failures in handling data moving in and out of the mobile environment securely. Unvalidated API data, populating UI elements, sensitive data logged without masking, etc. And then, of course, application programming interfaces, APIs. The unseen conduit. APIs are the glue of modern apps. Insecure output here is subtle but powerful, the most common issue. Excessive data exposure. An API endpoint returns way more data than needed the whole user object, including password hash, admin flags, internal IDs. An attacker just calls the API directly, bypasses the UI, and grabs everything. A failure of least privilege in output. Plus, an API can be a vulnerability propagator. It might reflect user data in JSON XML without sanitizing. Maybe not an API flaw itself, but if the client app consumes it and renders it without encoding. XSS in the client originating from the API's insecure output. That responsibility gap again. The OWASP API Security Top 10 directly calls this out, especially with API 3.2023 Broken Object Property Level Authorization, where APIs leak sensitive object properties.
It's really clear that as AI engineers, we're not just building isolated models, we're building components within these incredibly complex ecosystems. And every single point where data gets exchanged, web input, LLM output, API response, is a potential failure point if that output isn't handled with extreme care and, frankly, deep skepticism. That was a fantastic breakdown of where these flaws hide. Now let's make it even more real. So what does this actually mean for us, the people building these things day to day? What are the latest stats telling us about the real-world damage from insecure output handling? Are these just, theoretical possibilities, or are they genuinely causing major problems right now?
Oh, they are absolutely causing major problems. These aren't theoretical risks at all. They translate directly into widespread, costly, reputation-shattering security incidents, exactly the kind of thing no AI engineer wants their project associated with. And despite being, honestly, incredibly well-understood vulnerabilities in the security world, they remain one of the most persistent and damaging threats out there. Let's just look at the statistical landscape of injection vulnerabilities. The CWE Top 25 Most Dangerous Software Weaknesses list for 2024. It tells a story every developer needs to hear. CWE 79. Improper neutralization of input during web page generation, cross-site scripting, is ranked number 1, the single most dangerous weakness with a score of 56.92.
Number 1. Still.
It's still number 1. Not because it's novel, but because it's so frequent and the impact is so severe. And other injection types, Squillian, CWE89, OS Command Injection, CW78, they're consistently in the top 10 too. This isn't just a list. It highlights a systemic failure across the industry in managing data flow securely, especially when LLMs might be influencing or generating that data. The OWASP Top 10 from 2021 echoes this. XSS got rolled into the broader AO3.2021 injection category, but the data behind that report, it showed that a staggering 94% of all applications tested had some form of injection vulnerability.
94%. That's almost everything.
Pretty much. It points to a massive industry-wide gap in handling data correctly somewhere in the lifecycle. And if you look at Verizon's 2025 Data Breach Investigations Report, basic web app attacks, which explicitly include XSS and SQL, were the root cause for 12% of data breaches. That's up from the previous year. Attackers are still successfully hitting these foundational flaws, often as their way in. Now, consider the human and financial cost. The scale is alarming. In 2023, over 3,200 publicly reported data compromises, affecting around 353 million people. That's a 78% jump from 2022. 8 of the top 10 biggest breaches in 2023 linked directly to vulnerabilities in application attack surfaces. Together, they expose nearly 1.7 billion records. And when you look at the root cause, The human element is involved in 74% of breaches. A huge part of that is insecure software development. A 2025 survey found 67% of UK tech leaders admitted their company had breaches in the past year specifically because of insecure coding. That's a direct line from developer errors and things like output handling to real-world devastating incidents. The financial costs, also dire. The average cost of a data breach hit a record $4.88 million in 2024. That includes detection, response, lost business, regulatory fines, a massive incentive to get this right up front.
It really is a striking paradox, isn't it? These vulnerabilities are often called solved problems in security circles. We know how to fix them, yet the numbers clearly show they're a major and even growing threat. And here's where it gets really interesting. It strongly suggests it's not primarily a knowledge gap among security pros, but a critical implementation gap, a training gap, a prioritization gap within development teams. And this has got to be amplified by the constant pressure for speed, rapid feature delivery, and the sheer complexity of modern systems, especially when you throw unpredictable LLM outputs into that mix.
Exactly right. The security community understands XS, SQLi, command injection inside out. We know the defenses, yet breaches keep happening. It points to that disconnect. Factors. Intense pressure in agile environments, security reviews get squeezed, lack of mandatory continuous secure coding training, especially on new tech like LLMs, and the complexity of distributed systems creating those responsibility gaps where no single team owns the end-to-end data security. Tackling insecure output handling is as much about culture and process as it is about code. It needs leadership buy-in. Let me give you some quick case studies in exploitation just to drive this home, especially for AI engineers thinking about their own systems. Revoluters campaign, 2023. This group hit at least 65 websites, stealing over 2.2 million records. Critically, they use both SQL injection and XSS. Shows how attackers chain these flaws, SQL to get data, XSS to compromise users interacting with the site. It's often multi-stage. British Airways breach, 2018. Very high profile. 380,000 customers hit. Caused by an XSS flaw that let attackers inject a card skimming script into the BA website. It stole payment info in real time. Huge fines, massive reputation damage, social media platforms, Twitter and Facebook, even the giants struggle. Both have had historical XSS issues leading to account takeovers and worms. More recently, Twitter's 2022 API vulnerability exposed data for initially 5.4 million, later revised to over 200 million users. Facebook's had huge API data scraping incidents affecting hundreds of millions. Shows API output security is just as vital. Fortnite, Epic Games. An XSS flaw on a legacy subdomain, among other issues, allowed account takeovers. Accessing personal info, in-game currency, even listening to chats. Over 200 million accounts potentially exposed. Shows even non-core assets need secure output handling. These aren't outliers, they're part of a pattern. For AI engineers, these are cautionary tales. If traditional data flows are this leaky, how much more risk do unpredictable, potentially code-generating LLM outputs pose if not rigorously secured? The stakes are definitely higher now.
Those examples really hammer home how severe and persistent these vulnerabilities are. Okay, so given this very real ongoing threat, how do we actually find these flaws in our systems? Recognizing the complexity, especially with AI woven in, it sounds like detection needs a really methodical, multi-layered strategy. As you said, no single tool is going to cut it, right? What does a robust detection plan look like?
You're spot on. A multifaceted approach isn't just nice to have, it's essential. We need to blend different techniques throughout the development lifecycle, understanding what each does well and where its limits are. Let's start with static application security testing, SAST. This is white box testing. It looks directly at your source code, bytecode, or binaries without running the application. For insecure output handling, SAST shines at data flow analysis, often called taint analysis. Here's the basic idea. 1. Find the sources. The tool identifies where untrusted data comes in HTTP requests, form fields, environment variables, and critically for AI engineers, any prompt input to your LLM, or any data retrieved from external sources, databases, APIs, regdocs that feeds into the LLM's context. This data gets marked as tainted. 2. Track the taint. It follows this tainted data through your code, variable assignments, function calls, data structures, even how it might be used in prompts sent to an LLM. It's looking for paths where the data isn't cleaned up. 3. Identify the sinks. SAST knows about sinks, security-sensitive spots where tainted data could cause harm. For output handling, sinks are things like writing to an HTML response, executing OS commands, os.exec, building SQL queries, db.queries, or even just printing data that might end up in a UI or log consumed elsewhere. 4. Flag vulnerabilities. If SAST finds a path where tainted data reaches a sink without going through a known sanitization or encoding function, it flags a potential issue.
Strengths and weaknesses.
Strengths. Early detection in the IDE, in CI/CD. Immediate feedback. Can scan 100% of the codebase. Pinpoints the exact file in line. Weaknesses. Can have high false positives. It lacks runtime context. Might not understand framework magic. Misses configuration errors or runtime-only flaws. Can struggle with dynamic code. Ideal stage. Design and development. The big challenge for AI folks. Traditional taint analysis might miss cases where the LLM itself generates malicious patterns not directly traceable to tainted input. The LLM can be the source of new taint. Next up, dynamic application security testing. DAST. This is black box. It interacts with the running application from the outside, like an attacker would. For output handling, a DAST scanner typically. 1. Crawls. Discovers pages, forms, URLs, API endpoints by following links, submitting forms, analyzing traffic. For LLMs, it might try to find chatbot interfaces or API endpoints accepting natural language. 2. Injects payloads. Tries known malicious inputs and discovered vectors, things like script alert, XSS script, or SQL injection strings. For LLMs, this might involve sophisticated prompt injection attempts designed to trick the model into generating malicious output, which the DAST tool then looks for. This requires some intelligence in the DAST tool itself. 3. Analyzes responses, looks at HTTP responses, page content, the browser DOM for signs of the injected payload being reflected or executed. If it finds the payload or parts of it in a dangerous context, it flags a confirmed vulnerability.
And the pros and cons here.
Strengths. Very low false positive rate. It confirms exploitability. It's language framework agnostic. Finds one-time and configuration issues. SAST misses. Weaknesses. Detects late in the cycle. Needs a running app. Coverage is limited to what it can crawl, might miss hidden functionality. Can't pinpoint the exact line of code. Ideal stage. Testing and staging. Then we have manual security code review. This is a human expert systematically examining the source code, often focusing on critical features or high-risk areas. They'd manually trace data flows, understanding nuances tools miss, verify context-aware encoding is correctly applied everywhere, assess business logic, especially around how LLM outputs are used, check secure usage of third-party libraries.
Seems thorough but slow.
Strengths. Highest accuracy, deep contextual understanding. Great for complex logic flaws, race conditions, sophisticated injection missed by tools. Especially good for bespoke LLM integration logic. Weaknesses? Yes. Slow, labor-intensive, expensive. Doesn't scale easily. Highly dependent on the reviewer's skill. Ideal stage. Pre-production and post-deployment. Used strategically. Finally, manual penetration testing. This combines external probing with human intelligence and creativity, often using specialized tools. The tester actively tries to break the running application, probing inputs, analyzing responses and contexts, crafting custom, often obfuscated, payloads to bypass filters, trying to chain vulnerabilities, e.g., use XSS to steal an admin cookie, then use that for privilege escalation. For LLMs, this means clever prompt injection to elicit bad outputs and exploiting how they're handled.
The most realistic tests.
Strengths, yes. Most realistic assessment against a skilled attacker. Finds complex chain flaws. Demonstrates real business impact. Weaknesses. Expensive. It's a point-in-time snapshot. Happens late in the SDLC. Ideal stage. Pre-production and post-deployment.
It sounds like there's definitely that vulnerability gap you mentioned. SAST misses context, DAST misses coverage. Thinking about something like DOM-based XSS, where client-side JavaScript messes up writing to page, both automated tools might struggle there, right? Especially if LLMs are generating client-side code.
You've hit on a perfect example. DOM-based XSS is notoriously tricky for automated tools. The server might send perfectly safe data, maybe in JSON. But the flaw is in client-side JavaScript that later takes that data and unsafely injects it into the page using something like element.innerHTML includes untrusted data. SAST often struggles to analyze complex client-side JavaScript effectively, especially dynamic flows. DAST might not trigger the exact sequence of user actions needed to hit that vulnerable JavaScript path. And yes, if an LLM is dynamically generating client-side components or JavaScript snippets that interact with the DOM, it gets even harder for automated tools to predict and test all possible unsafe interactions. This absolutely underscores why a comprehensive strategy must be layered. You need the breadth of automated tools combined with the depth and context awareness of human expertise. For AI engineers dealing with these complex systems where LLM outputs add new dynamic vectors, this layered approach is non-negotiable. SAST for broad coverage early, DAST for exploitability checks later, and manual review plus pen testing for the subtle, context-dependent flaws that only humans, frankly, can reliably find, especially in that unpredictable LLM interaction space.
Okay, so we know the risks, we know where they hide, and we have strategies to find them. Now, let's flip to the proactive side. How do we stop these problems from happening in the first place? What does this mean for you, building these systems, particularly AI-powered ones? How do we move from just fixing bugs to actually building resilient applications by design.
Yeah, prevention isn't about finding one magic solution. It's really about building a defense-in-depth strategy, an ecosystem of controls that reinforce each other. It requires secure design, robust coding, runtime protection. For AI engineers, it means embedding security thinking throughout the entire development pipeline. The foundation has to be adopting a zero-trust philosophy for outputs. Seriously, this isn't just jargon. It means every single piece of data leaving your application needs to be treated as untrusted and potentially malicious for whatever is going to interpret it next. Doesn't matter if it came from a user, your trusted database, another internal API, or even your own carefully crafted LLM. Assume it's hostile until proven otherwise for its specific destination context.
So ingrain that skepticism in the team culture.
Exactly. It needs to be part of your secure coding standards, part of how developers think by default, especially for AI engineers who might feel tempted to trust their intelligent model's output. Don't. Next, robust validation and standardization are crucial early layers, even if they aren't the final defense. Input validation. Your first line of defense, right where data enters. Enforce strict rules before you process or store it. Type, length, format, range. Use allow lists, whitelists. Define what is good. Don't try to guess what's bad. Deny lists. This stops many injection attacks cold. But remember, it's not enough alone because data can get tainted later. HTML sanitization. Okay, sometimes you must allow users to submit rich HTML, like comments with bold italics. Standard encoding breaks that. Here you need dedicated battle-tested sanitization libraries like DOM purified JavaScript or OS anti-sami Java. These don't just encode, they parse the HTML, build a clean structure, strip out all dangerous tags and attributes, script on-air JavaScript URLs, and only keep a pre-approved safe subset. Never try to roll your own HTML sanitizer with rejects. It's incredibly hard to get right and almost always fails. Use the established libraries. But the absolute cornerstone, the single most effective defense against insecure output handling, is context-aware output encoding. I can't stress this enough. The encoding method must perfectly match the specific location, the context, and the output where the data is going. One size does not fit all. It's dangerous to think it does. Different interpreters, HTML, JavaScript, CSS, URLs, have different rules.
And do this encoding server-side right before sending.
Always. On a trusted system, typically the server, right at the last moment before the data goes out to the client or the next interpreter. Let me give you a quick practical guide for common contexts. HTML body. Between tags like div. Use HTML entity encoding. Attacker inputs, script tallet, script enkidia, script and gwait. Displays as text won't run. HTML attribute, inside quotes like value. Use HTML attribute encoding. Input script tallet, script becomes end quote, script and gedal, alert one in text, will intect, alert one intect in technical. Prevents breaking out of the attribute. JavaScript string, inside quotes like var name. Use JavaScript hex Unicode encoding. Input script tallet becomes HTML alert 29 tallet treat. Treated as a literal string by JS engine. CSS value, inside styles like color. Use CSS hex encoding. Input red, expression alert 1, C alert pen alert 29, 21 by 29 alert 29. URL parameter, in query string like Q. Use URL % encoding. Input script alert script becomes 3 lead Cs for 23, 3 C 32, 32, 3 T script 3 fee or 3. Prevents interpretation as HTML script in the URL. Getting these specific encodings right neutralizes the threat by stopping the data from being seen as code in that particular context. Then, add content security policy, CSP, as a defense-in-depth mechanism. This is a powerful browser security feature delivered via an HTTP header. You tell the browser exactly which domains are allowed to provide resources, script styles, images, and what kinds of content are okay.
So even if XSS gets injected, CSP can block it.
Often, yes. A good CSP can massively mitigate XSS impact because the browser will just refuse to execute a script if it violates the policy. Key directives, script-src, restrict script origins, use nonces, object src, none, block plugins, base or here self, prevent base tag hijacking, frame ancestors, none self, stop clip checking. Pro tip, start implementing with the content security policy report only. It logs violations without blocking, letting you fix things before breaking your site. Okay, now for the AI engineers in the audience, let's talk advanced mitigation for modern systems, specifically LLM-specific guardrails. Strict output validation. Treat all LLM output as fundamentally untrusted. Before you use it anywhere, validate it rigorously. Check against a predefined schema, like using Pydantic for structure or JSON schema validation. Use content filters, open source tools, or commercial APIs like Guardrails AI to screen for harmful content, PII. Known malicious code patterns. Never, ever assume the LLM's output is safe or compliant just because it came from your model. Sandbox execution. If you must execute code generated by an LLM, e.g., Python for data analysis, maybe DSL. It absolutely has to run in a highly restrictive, ephemeral sandbox. Think temporary Docker containers with no network access, Firecracker micro VMs, or maybe WebAssembly, WASM environments. Contain the blast radius. Prevent it from touching your host system or critical infra. Human-in-the-loop review. For any high-risk action triggered by LLM output, deleting data, sending customer emails, making financial transactions, build in a mandatory human confirmation step. This adds crucial oversight for unpredictable AI actions. Also, really lean on leveraging secure frameworks and libraries. Use modern web frameworks, React, Angular, Vue, and server-side templating engines, Jinja 2, Timeleaf, Handlebars, why? They often provide automatic, context-aware output encoding by default.
Making the secure way the easy way.
Exactly. Train developers to use the safe methods these frameworks provide, and critically train them to avoid the dangerous escape hatches like React's dangerously set inner HTML or raw output functions and templates unless absolutely necessary and paired with rigorous specific sanitization. Finally, adherence to security standards helps pull this all together. Align your practices with established guidelines, NIST, SANS, frameworks like the NIST Cybersecurity Framework, CSF, or controls in NIST SP 853 provide a solid foundation for secure design, monitoring, and risk management, which inherently helps combat insecure output handling.
That really does paint a picture of an ecosystem of reinforcing controls. It's not about one thing, but building resilience layer by layer from education and secure defaults and frameworks to testing, runtime hardening like CSP, and crucial checks like sanitization and LLM output validation. It's a holistic approach, accepting that some things might slip through early defenses, so later layers need to cache them. #outro.
Yeah, and if we connect this to the bigger picture, insecure output handling isn't some minor edge case. It's fundamental, it's pervasive, it's a core failure in managing data across trust boundaries. The consequences, they range from embarrassing to utterly catastrophic mass account compromises via XSS, complete server takeovers via RCE. And what's truly troubling, as you said, is the paradox. We know about these vulnerabilities. They consistently top the most dangerous list, yet they continue to be a primary way attackers get in. This points squarely at a failure of rigorous implementation in our development practices, not a lack of knowledge and security. And LLMs, with their dynamic, unpredictable outputs, they're acting like massive amplifiers for this existing problem, potentially turning poorly handled outputs into devastating attack vectors.
Exactly. This raises an important question for all of us, particularly for you listening who are AI engineers. We've laid out a holistic strategy: continuous education, secure design using safe frameworks, robust validation and sanitization, layered automated testing, SaaS-DAST, runtime hardening like CSP, critical human oversight through reviews and pen testing, and those crucial LLM-specific guardrails. But let's leave you with this final provocative thought. In an era where AI can generate not just text, but potentially executable code, system commands, or even subtle misinformation that warps business logic, the responsibility for securing the output is greater than it has ever been. How will your team ensure that the powerful, often unpredictable outputs from your AI models don't become your next major security incident? And maybe more importantly, how can you personally champion making never trust data sent to an interpreter the absolute unwavering mantra, not just for web dev, but for the entire field of AI development? It's a continuous journey, this security work. And your role as engineers building these incredibly powerful intelligent systems is more critical than ever in ensuring they benefit us, rather than becoming tools that compromise us.
It's definitely a deep and complex area demanding constant attention, continuous learning, ongoing vigilance. Those are really our best defenses as things keep evolving, especially with AI. The future of secure AI really depends on us getting this right.
Couldn't agree more. Thank you so much for joining us for this deep dive today. We really hope you take these insights, apply them, and help build safer, more resilient AI-powered applications. Until next time, keep diving deep.